Our next application of the combinatorial strange is due to Alon. Actually, this was proved by Alon, Friedland, Kalai in 1984, but later it was proved by Alon again with different proof. So this is the theorem. So Alon, Friedland, and Kalai in 1984. It says the following: every multigraph. So multigraph is a graph with possibly some parallel edges with the average degree at least more than 4 and the maximum degree most 5 contains a 3 regular graph, a subgraph. So whenever you have a graph whose average degree is big but maximum degree is small, then you can always find a 3 regular subgraph. And so this proof is due to Alon in 1999. So how do we prove that? And here we're going to use the permanent. I mean, let's see what happens. We're going to use the combinatorial strange. So let M be the V by E instance matrix of G. Over the finite period of size 3. So what that means is M is a matrix where the rows are indexed by vertices and columns are indexed by edges. Then you put 1, 1 if a vertex is the Z instant with the corresponding, if an edge E is instant with the corresponding vertices on the row. And let's say M is the number of edges and N is the number of vertices. Now we want to take the subgraph, and subgraph means we need to choose an edge or not, right? So we have to select an edge or not. That's the what we want to do. So for an x in E to F3, right? So it's like, what does that mean? That means x is a function. Is this a better way? Or you can think of it as, think of the variables x1, x2, xm. These are variables where the m is the number of edges, and you can imagine that edges are numbered from 1 up to m. So let's define f of x is the product for each vertex v. Yeah, so let me say it this way. Let me say, so for x in GF3 to the E of G, right? Yeah. So we multiply some of the xe squared whenever E is instant with a V, and then minus 1 minus xe. I mean, I'm writing E for E of G. So so this is my polynomial. What is this doing? And we will set LE to be the 0 or 1 for edges in E. Now, if we look at this polynomial, now what does that mean? Now, observe that G squared is always 1 or 0 if G is not a multiple of 3, and if G is a multiple of 3, then G squared is 0, right? So this term here just measures whether or not this is multiple of 3, right? So if this is multiple of 3, then this becomes, then this becomes 0 modulo 3, so 1 minus 0, so then it becomes 1, the product of that. So this part, let me write it down, this part is 1, 0. So this is 1 if this number is 0 modulo 3 for all vertex V. So what does that mean? That means for each vertex, number of edges incident with it is a multiple of 3. And 0 otherwise, that means there is a vertex, so that the number of edges incident with it is not a multiple of 3. So then we have 0, 1 and 0. And what is this? This means for every edge, this is 1 if all x's are 0. And this is 0 otherwise. So that means we're gonna subtract 1 if x is completely 0, and otherwise it's gonna be 0. So what does that mean? That means f of 0, 0, 0 thing, this is trivially 1 minus 1 is 0. Okay? And fx is non-zero if and only if, and let's say xi is in L E, that means for each vertex V, the number of edges where E is incident with V is multiple of 0. And since the maximum degree is at most 5, if it's multiple of 3, then it's going to be either 0 or 3. And now you take the subgraph H, define subgraph H, the subgraph of G consisting of edges incident, edges such that xe is 3. No, not xe is 1. So then H has at least one edge because of that, because fm 0, 0, 0, 0, this is zeros, and H is 3 regular, right? I mean, I'm only collecting edges, vertices instead with some edge, some edge whose value is whose value is 1. So that's why it's 3 regular. So it's enough to find the assignment xi in Li so that f of x is non-zero. Now this is given by the combinatorial Null's-Lenses, right? Because what is the coefficient of the product of xi? Because we have only 2 choices, we need to look at the product of xi. What is the coefficient? I mean, of course we have to look at the degree. So degree, what is the degree? So here the degree is the this is the okay, let's look at this way. So degree of the product of 1 minus sum of xe squared is for each vertex v, we are adding twice the degree of this vertex, right? no. It's just twice number of vertices. Yeah. And degree of the product of 1 minus xe is twice, it's the number of edges. Now, since the average degree is bigger than 4, so the average degree is twice e divided by number of vertices. This is bigger than 4. So that means twice v is less than number of edges. So that means the degree of f is precisely number of edges. And the coefficient of the product of x, oh, I should say not this one. Let me, product of xe, right? I should say xe here. Degree of that is just minus 1 to the number of edges, which is non-zero, modulo 3, right? So therefore there exists x1, xi in Li, so that f of x is non-zero modulo 3. And that's it. That's the proof. This is by combinatorial Nostranza. Okay.